All right, first one, let's look at ladder problem. This is a really common one. You see this a lot in math, and there's a lot of similar problems you can do that are kind of the same relationship, same mathematical relationships, right? So we've got a 41-foot ladder leaning against a flat vertical wall. The base of the ladder is pulled away from the wall along the horizontal ground at a constant rate of 2 feet per second. How fast will the top of the ladder move down the wall when the base is 40 feet from the wall? Right? Okay, so we need to identify, we need to label some variables, some things that we can add to our snapshot list, right? So this is going to be just a representative frame in the movie. Everybody sees what's going on here. I just drew little pictures. It helps to draw pictures on these. So here's the vertical wall, there's the horizontal ground. We're just pulling the far edge of the ladder away from the wall, and the ladder's going to be slipping down the wall, right? Okay, so what variables might we use?
So the rate at which it's going away from the wall, would you call that x dot?
So yeah, so we need to, if we're going to call that x, which makes sense. So we could call this distance down here. Let's call this distance x, and then that distance y, how about? And those are variables, aren't they? They're things that are changing. Now, what are we going to call this?
H for hypotenuse.
See, I wouldn't put a symbol on it, because then it tricks you into thinking it's a variable, and it's not. So we make it 41. Well, whenever there's a constant, remember, we're actually going to put the number into the drawing so we can see right away that it's not a variable, right? So the length of the ladder stays the same, that's constant, right? So based on our picture, and I guess if we really want to be nice about this, we'd probably do that, right? Make a right angle. So what are our snapshot values then?
X dot equals 2 feet per second.
Okay. The bottom is being pulled away from the wall, so x is increasing. Everybody agree? It's increasing at a rate of 2 feet per second. Good. What else are we given?
40.
X is 40.
Y equals.
And okay, and we could, so there's another issue we can, so hold that thought. We could add more stuff if we need to, now or later, right? We can always go back and restock this step if we need to add more stuff. What are we trying to find? Y dot. So right away, are you going to expect Y dot to be positive or negative?
Negative.
Negative, because it's getting smaller, isn't it? Right. Okay, so, comment, question?
No.
Okay, so there's step one, right? There's our snapshot variables. What's step two?
Parent equation.
Parent equation. So what's the obvious parent equation that's going to relate x and y in this picture? Sure, it's a right triangle, right? So step two, let's label these. So here's step one. I'm not going to, that's snapshot variables. Step two, parent equation. X squared plus y squared equals 41 squared. Okay? So there's our parent equation. Okay, that's good, right? Pretty simple. What's next? Yeah, so now finally, once we've got a good parent equation, we've got our snapshot values, then we're actually going to introduce the calculus by differentiating implicitly with respect to t, right? We want to get rates out of this. So step three, what's the derivative of x squared with respect to t going to be? X dot. Good. Plus, everybody see that, right? Equals 0. Good, because that's constant. Very good. So then we could make things simple. How about if we divide both sides by 2? Get rid of those. We're trying to solve for y dot, correct? Okay. So step 4, we can kind of move on down to step 4 now. If we're going to solve for y dot, all we're going to do is subtract that to the other side and divide by y. So the math's pretty easy on this one. And a lot of times, what you'll find is you've done the hardest calculus that you're probably going to do all year in terms of like cranking out hard derivatives. We're getting into kind of the application phase now, which I think is the fun phase. And when we do these applied problems, you're leveraging your knowledge of calculus, but seldom are the problems going to be that hard to do, right? Really, it's just the setup that's the challenge, and executing the process is the challenge. Usually the calculus is not nearly as hard on this, right? So y dot equals negative x dot over y. So what's our problem that Elton already Saw?
We have to solve for one.
We got options. We can either introduce, couple options here. We could either introduce another snapshot variable, which we can do. We could just solve for the value of y in this snapshot. Or if we wanted to, and that's what I would do, the other thing you could optionally do is you could take this equation right here and solve it for y in terms of x. Right. And if we did that, we would just get what y equals the square root of 41 squared minus x squared. And we could make that substitution if we want to, and then just use the existing snapshot variables, but that seems harder. It seems like there's more, don't you think? So we would just, this is a Pythagorean triple. Do you remember, is that how you do that?
Nine. No, I.
Oh, you did, okay.
I've seen others like, yeah, I guess it was, just didn't know that my was.
So y equals 9. If we solve that, if we just plug in, and sometimes when you're in the process of doing this, you might even like write, next to those variables above or below them, you could actually write the values if you want to at that point. Just to remind yourself that these are the snapshot values. They're not constants. I would circle them so I know that they're values of a variable instead of just numbers that were in the original drawing, right? So 41, square root of 41 squared minus the square root of 41 squared minus 40 squared is 9. So we can add that value, and then it's just a matter of plug and chug, right? So we end up with negative 40 times, that one ends up being times 2 divided by 9. And so we get negative 80 over 9. And what would the units be? B per second. Okay, good. Sure. And just so you know, I've been trying to be really good about this, and I'm not always, but I've been pretty good lately about this. I've been making time. Is that, yeah. So if you go to the Moodle Calculus site, just a reminder, if you go to instructional videos and notes, and you go to notes, this is like, there's the last, what was that, like yesterday or day before? Right? There's everything we did, right? It's all right there in all its multicolored glory. Yep. Okay, so let's try another one. That was good. You guys are getting this. So this one we got to kind of make a drawing, right, that's going to represent this. So an airplane is flying at a constant elevation of 6 miles at a constant speed of 400 miles per hour on a flight path that will take it directly over a radar tracking station. Okay? So this is implying it hasn't gotten there yet, right? So it's flying towards this. We can start to make our drawing here maybe. So here's the level ground. Call that R for radar, how about? And here's the plane that's flying in this direction, right? So it's eventually going to come right over the top of this thing. So at what rate is the angle of elevation formed at the station between the ground and the plane changing when the plane is approaching the station at a horizontal distance of 10 miles? Okay. So then this is kind of what we're trying to do, isn't it? We've got this. Looks like another right triangle problem, doesn't it? Right? So I can label some stuff. What do you think? What am I going to call this? 6, because that's a constant, right? It's flying at a constant altitude. So 6, and our units are just miles and hours, it looks like, right? I won't write the units up on my drawing. What might I call this? I'd call it X, right? It just fits. And the only other variable we're looking for is theta, and that's that angle of elevation between the line to the plane and the horizontal ground, right? Okay, so there's our drawing. What are our snapshot values then?
X is 10.
So X is 10. Now what about this one? This one is, you have to be very careful with that. Everybody agree? Negative 400, because if it's flying at a constant speed of 400 miles per hour, that's distance over time, right? and it's flying horizontally, so that must be the rate at which x is changing. That one's, to me, that's just a little trickier to see, but it makes sense. And then because the distance is getting smaller, it's negative, right? So we get x dot equals negative 400, and we're looking for what? Theta dot. Good. Right? So what's going to be our, our trig function this time? We have some options, I guess. Say it again. Tangent would be one, right? Or cotangent. We've got a right triangle here, and theta is, we want to write it in terms of the two things that we know something about, right? The variable, which is the adjacent side, and the constant, which is the opposite side, right? So now let's look at these both, and they'll both work, but it makes sense here to kind of think about this in terms of the derivative you're going to be doing. Is one of them better than the other? And a lot of times I think people just, like even the books will just sort of charge through this and use tangent. But bear with me on this. So there's step one. Here's step two. We could either say, if I write it in terms of tangent, what's tangent theta going to be? 6 over x. Good. If I choose to use cotangent, what's that going to equal? Okay, now, which of those is probably a better derivative to do? Cotangent, yeah. Because then I've just got a 1/6 constant. You see that? They don't have to do like a generalized power rule where I'm doing x to the minus 1 and I have to use chain rule, right? So we'd probably just use that one, I would. So there's our parent function, step 2. Step 3, we'll just differentiate, right? So what's going to be the derivative of cotangent theta with respect to t?
Negative cosecant squared theta dot.
Negative cosecant squared theta, and you guys are all, everyone got hundreds on this, so I know you know that, times theta dot, right, equals, and then this becomes a really easy one, right, because the 1/6 I can just pull out front, so what's the derivative of the right side? Yeah. Okay? And all we're trying to do is solve for theta dot, right? So then step 4, we're just going to isolate that. So that means it's going to become negative, and I'm going to divide by cosecant squared, right? Oh, what's the reciprocal of cosecant? Sine, right? So I could just write that as negative sine squared theta over 6 times x dot. Well, either order, doesn't matter, right? Okay, and so now I just have to plug and chug. Okay, so what's the problem with my answer here? I don't know theta, right? So what are my options? I could solve for theta in my snapshot, right? We're taking the situation where x is 10, and so we could say, okay, we can just define theta as the arctangent of 6/10, okay? And that's fine. And then that's just a number. We can just plug that in our calculator, whatever we're using, just in parentheses for theta, and it's going to give us the sine of that number, whatever the calculator says it is, squared. That's fine. Or the other thing we could do is we could build a reference triangle out of this, right? We know that here's my triangle. So if we make a reference triangle out of this, we already know that that's 10 and that's 6. So this is going to be what, the square root of 136? Okay. And sine, if that's my theta, I can describe sine as just a ratio, right? Sine is opposite over hypotenuse. So I could just say 6 divided by that if I want to also. Either way. I usually do it this way, so I don't have to mess around with having to find the arc trig function on my calculator. I would just write it as a reference triangle and say negative 6 squared over 6 times x dot, we said was negative 400. And that's just gonna give me some number, right, some decimal. Okay, makes sense? And what would my units be? Miles per hour. Yep. Oh, hold it. No, we're doing theta dot, so it's gonna be radians per hour. Yep. Okay. So would you expect that to be probably a big number? I would think it might be fairly big, because if you think about, well, not super big, I guess, but per hour, I mean, that's a lot of radians in an hour, isn't it? Right? So it's probably gonna be a decent sized number, I would think. Right? In an hour, that plane's gonna go, it's gonna go a long ways. It's gonna span a lot of radians, right? Okay. Do we have time? Hey, this is a fast one. We can do this one. Then I got one for tomorrow. I think we're good. So this is just a, this is, and you see these a lot. So it's just a, we did the sphere one in class, right? This is just an example with a cube. Right? So this is, this is a really common, like this would be if you were, if a metal cube were heated up so that it was expanding because of the heat. That would be, this would be something that would apply to that situation. So all edges of a cube are uniformly expanding at a rate of 4 centimeters per second. We could draw a picture here, but our picture is going to be pretty straightforward. I mean, what's the only variable? X, we go X or S, whatever you want to call it. What do we get? Oh, okay, so there is one little wrinkle here. We don't know. But what did they tell us? They tell us when the surface area of the cube is 24 square centimeters. So we don't know X directly. What is it we're going to build to fill that in? But what is it that we're trying to find? V dot. Okay. So we know X dot too, don't we? So we know, I'll put that there. So we know X dot is positive 4. But that's probably not quite enough, right? Because our parent equation is clearly going to be the volume equation. V equals just X squared, right? Or X cubed.
Combined with the surface area.
Right.
Yeah, we can solve for X with the surface area.
So what can we do with that, right? We got to be able to fill in some other stuff here. When I differentiate, I'm going to get my V dot and my X dot, but I'm also going to get an X in my answer, correct? Everybody see that?
Well, again, we put the 24 cubic square centimeters up on the snapshot value,
We can use the surface area formula.
Okay, so one thing we could do is we know that the surface area is 24, and what is the surface area equation for a, 6 times each face is X squared, right? So we know that S equals 6X squared equals 24, so we can just solve for X, right?
Yeah.
We could turn this condition, if we wanted to, we could turn that condition into a corresponding X value, right? So if I divide by 6, X squared equals 4, so we're going to take the positive result, right? You obviously can't have a negative dimension for a cube. So X equals 2, we can add that up here. And now this gets really simple, right? So now if we differentiate, V dot equals, okay, and then it's already set up, so we can just plug and chug, right? Then we get 2. Was that 2 also? Well, that was 4. So, yeah, 12, 48?
Yeah, 48.
What should the units be on this?
Cubic centimeters. There's no centimeters
Per
second.
second, yeah, right, because we're doing, seconds are our time, and centimeters evidently are what we're measuring length in, right? So we get 48 cubic centimeters per second. Okay? Make sense? Okay. All right. That's about all I got in me today, I think. I will update notes in the video right now, so we're done.